All right, so welcome to another talk of zfit today, but this is mostly focused actually on TensorFlow 2.0, and I won't spend too much time on zfit itself. So just if you haven't heard what zfit is or haven't seen the tutorial before, I think so it's a model fitting library in pure Python, and the two core features are really that it's a well-defined workflow with a lot of flexibility in there in the model building. And it's well integrated in the whole Python ecosystem. It has a limited scope, as we've also seen before a little bit, builds a lot of other packages. And as a core idea, it builds on TensorFlow as its computational backend, in the sense of building on top of another package. This means that to try to delegate as much as possible of all the optimizations that we need to do to TensorFlow itself. This is basically the core idea of it. And this will also be the focus of my talk today. Before I go, as also promised before, I'll just have a small note on general changes. So zfit evolved, and there are many, many small changes. For example, the docs changed and printouts improved, as you've also seen in the notebooks and so on. What is surely worth mentioning is that there are more and more shapes being added, convolutions coming out in the next few weeks, and KDE is now there, as you see in the yellow part. We have clearly improved the fitting stability using penalties and doing more checks. And also toys, as you see in the lower right, for example, this is a toy model work now quite cleanly. Also, we've improved spaces on combining them, on handling arbitrary ones, which also allow us to reach out into other fields like amplitude, fits, and so on. The main improvement, the main change, also the main work went in there, was to switch to TensorFlow 2.0, because before it was TensorFlow 1. A further improvement is a numerical gradient and some smart JIT compilation caching, because TensorFlow 2.0 basically supports JIT, as we will see. What this means is that we have now a very easy way to be fully integrated with Python and NumPy. I think it was on the large PyHEP that I think Jim asked the question. I have a large Fortran-based function and I want to implement in zfit, and the answer back then was, you can basically kind of maybe do that, and while the answer now is no problem, you can do that. So before we start with the more fun part, and I'm going to show you in the notebook some thing about TensorFlow 2.0, we'll first just remind you, of everyone who knows about TensorFlow 1, what a pain it was. So back then you had to really define a graph. You had to say, I want to have this element and this element together, and what you get then is a symbolic tensor, which is not yet the result, but we have to execute it. And then you see you can do stuff like the for loop in the left lower corner that just adds up things, and yeah, it creates too many operations. So basically you're doing the wrong thing there. What was also there is, so we need to do this in the right way. Also, inputs were a pain, because how to input things, there was some stuff like placeholders, and this was also not the right thing to do, because they explicitly wrote this is not the way to go. Some are different, but we don't know either how to do it and such. So yeah, sessions. And in short, what actually was always going on is you just had an object that you wanted to say, now run with these inputs and give me some calculations in return, which we would actually just call a function. And when looking through TensorFlow 1, TensorFlow 2, and development, some are resistant rather to go to TensorFlow 2. I was in the beginning a lot as well. And I found this nice quote, which brings it really on the point. TensorFlow 2 is a huge improvement compared to TensorFlow 1. And I'm going to show you how we can see TensorFlow 2 now. Before it was an exotic, odd machinery. if I'm saying TensorFlow2, just to be clear, because people usually TensorFlow, they confuse it with machine learning, and I think this has to do with machine learning. We are not interested in all this stuff. This is nice, but what we are doing is we really look just at the low-level functionality of TensorFlow, which is equivalent to basically NumPy. It's just math operations that are connected in an efficient way. So TensorFlow2, in very brief, this is now NumPy with a JIT like Numba. And that really covers, let's say, 90% of, if you want to get an idea what is TensorFlow or low level, how we're using it, that's it. There are still quite a few differences. For example, TensorFlow has, let's say, way more overhead in really calling a function below. It has different kernels, it has a whole registry. It can compile, merge different kernels, fuse kernels. It can still dispatch parallelly. It has some asynchronous stuff in there. It has some kind of its own intermediate representation and so on. So it usually takes longer for very small things. But in general, as you see on the left lower, that's a valid TensorFlow function, and it behaves exactly the same actually as with NumPy. What we've seen there is just a kind of eager mode that is now the default. That's actually the whole thing of it. It's like by default we behave like NumPy. And one of the great advantages is using this TensorFlow 2.0 that since it behaves like NumPy, exchanging the backend at any time, because this is also an often asked question, is now, let's say, fairly easy. It is not for free, but it is fairly easy because it already follows the same paradigm. It's not there because having switchable backends work for some cases, but for more complicated cases, it's a lot of work as well and a lot of cost. And this is not worth it at the moment, but it's pretty easy now to switch away, and I'll even show more why. I talked about the JIT part. What we see now on the lower right is what we would usually do in TensorFlow, which is we would add a tf.function decorator. And what this does is it basically restores somewhat the behavior before. So this now goes through and catches all the TensorFlow operations. Side note, I wrote autograph equals false. This is a feature that can't be used and that converts some Python code into TensorFlow, but let's forget about that for the moment being, and overall, let's say it just cares about the TensorFlow functions. So what it does is, if you have a function now, and you put this decorator there, I think this works very similar to as Numba works, as Julia, and all these languages work. So you give an input, it replaces by a more symbolic tensor. It does all the calculations using the symbolic tensor to know what it's going to be. It just records the TF calls and remembers the input. It stores this graph. There's, you could say, low-level representation, but it's actually not a real low-level representation. It's still a high-level with the graph. It remembers this, given the d-type, sometimes a shape, and this is also important to note. This does it only for tensors, generalize it. If you give him Python objects, which you can too, it checks for the equality, meaning it doesn't cache for different, so it creates a new graph for each different Python object, which is somewhat NumPy and Numba without Python compilation. And this means we cannot just convert a for loop or an if, but TensorFlow provides so stuff to create explicitly for loops and if whiles with TensorFlow language. The good thing on that is that this doesn't have black magic in there. So you know the Python code basically runs once, and it is just there to define your computation running in TensorFlow. This, of course, has also limitations. It's a certain trade-off, but it makes things way cleaner in a way and allows to have thousands of lines of code to just stick together your computation. So why is this graph so important? Basically, because the knowledge about the d-type and shape and all the dependencies is contained there. We can also add sometimes additional information, like we can specify a more specific shape, we can guarantee that something is constant such. And there's the grappler in TensorFlow, which is a graph optimizer. This looks for common sub-expressions, this can do simplifications, and so on. So instead of a computational graph, it's still a very high-level representation, and let's say easy to few stuff to optimize that. And the parallelization is maybe the strongest point from performance measurements that I see with TensorFlow. Having a graph, it is fairly easy to parallelize. TensorFlow even runs usually a small simulation of your graph to check whether it's worth to split it up to multiple CPUs. But in the end, the graph is just a stitching together of all the TensorFlow graphs, of all the TensorFlow operations. So I'm going to share now our screen, which is basically a little introduction into how to use TensorFlow or abuse it to do some high performance computing. I mentioned before that it's basically NumPy-like, and this is how it looks like. So if you haven't heard of TensorFlow and you think it's machine learning, you see here, this looks very, very familiar. And what we have here is an eager tensor. This is now TensorFlow2. Before we had this abstract tensor that no one can deal with, and this now is just basically a wrapped NumPy array, which means we can just also get an NumPy array directly from it. And it also works as we would expect it if interacted. We can even now feed this directly into NumPy. So random1 is an eager tensor, something that before was completely impossible and it would have screened for sessions and anything, but this is just a wrapped NumPy array now. If we give that to a NumPy function, it returns us a NumPy array. So anything like zfit that uses tensor inside and just returns tensors, these are now eager tensors, like integration and stuff, can directly be used afterwards with NumPy. And you don't get any disadvantage of that. If you don't even need to care about any graph and all these things. Of course, slicing and expanding dimensions, this is all just some NumPy-like magic, and the main point is this all works. But in general, we don't want to use NumPy directly. As I've seen before, we have all these equivalent functions. Some are named differently slightly. What is to say in general, I regard this as quite a strong point actually of TensorFlow, sometimes a bit annoying. It is more picky, or let's say it requires you to be more explicit sometimes about which axis to reduce over, or the shape itself between scalar and vector, or the D-type. So you will usually have a lot of D-type complaints. How this works, I'll show you very nicely. This is something that you would expect to work. The logarithm of 5 command, take that, doesn't, because what we see here, I talked before about these kernels. When we call a tf function, then this dispatches to a kernel. And what this says is basically, these are my registered kernels, and I don't have one with integer. So we have to actually cast it. This can be slightly annoying. On the other hand, it's very explicit and very clear what is called when. And we see also here we have different kernels for CPU, GPU, and XLA, some kind of accelerated linear algebra, which is a project for fusing kernels and improving certain things. But now let's look at the JIT, the actually interesting part. We have here allo, which is a completely normal function. As I said before, there's no difference from feeling to NumPy. We can just call that and we get a tensor back, but it's a wrapped NumPy array. We can call it again. And what I've done here is, it's important to notice, is the print is a Python statement. Whenever we see running Python, it means that this line is executed. While tf.print, this is a TensorFlow operation. This is not executed when Python is run, but this is executed basically when the TensorFlow logic is run, which here, if students were eager, this is basically the same. However, if we now start decorating this, we have the same code as before, giving some x, giving some y. If I execute this once, we see we run Python, and immediately after, so it now built this graph, it caches this graph, and it runs the graph for the inputs. So that's why we see both of them, but these actually happen like after each other, in let's say, consecutive runs. If we do it again, we use now, and this is one thing I mentioned before, we use now Python object, and this is the problem. It builds now a new graph, because it doesn't realize that 1 and 11, let's say, are actually the same. You could use the same graph, but that's actually a good thing. So now it rerun Python, it rerun TensorFlow, which is like the pitfall to go in. How we really want to use it is here with tensors. I'm giving it now a tensor. It runs Python because it compiles it. It runs TensorFlow because I asked for the result. And now this is stored and cached somewhere. So if I rerun this now we don't have any Python code left anymore. What we have is just a graph. Anything that is Python dynamics that became basically static, that is just not there anymore. And this is illustrated here quite well. Now we have a function. We have again the print and the tf print. This returns 2 results. So we just have x multiplied by a random number sampled in NumPy or a random number sampled in TensorFlow. And this returns now completely different things if we run this with or without the tf function. If you would run it without the tf function decorator, then they will both return random stuff all the time. But if you run it like that, now the first time is it goes through, it prints this, it adds tf print as to the graph, it adds this operation to the graph, but doesn't do anything. Sorry, and it adds TensorFlow operation to the graph, but this one is really executed. It samples that, and random NumPy now has a fixed value for this graph compilation. While random TF doesn't have a value yet, this is a TensorFlow node. So what we get here is multiply the input by the effective number we sampled and multiply the input by the TensorFlow operation here. Meaning, if we now call this again, we see for the same argument, we see that the first return with the NumPy gives us the exact same result because that number is now fixed into the graph, while the other one varies. We can also take a factor of 2 in there. And we see again. This is a small pitfall if we go for this thing, but this was just to mention. Another nice thing in TensorFlow, which I think is not supported in Numba equivalently, is that it can have states, so variables, which mean we can now create a variable, and this is an object that has basically a getter and a setter on it, and is embedded in the graph. So what we have here is a function. We just give in some x input, and we multiply it by the variable. The variable is defined outside, but this is not a problem, because this is implicitly catched now by the function. So the function that we have now is the tf.function wrapped function, let's say, is aware once we create the graph that there is from the outside, there are captured variables in there. So if we execute this, we get 1, we get 2. Remember, our variable is set to 1, as we expected. We see again, first Python is executed. Here, Python isn't executed anymore because we have, again, the same tensor, same d type, so there's no need to rebuild the graph. But what we can do here now is we can assign a new value to the variable, and afterwards execute the function again, and our value has changed. This means we can change a compiled function, basically. There are global states that we can change. And this, sure, we can discuss about globals, but there are quite a few applications where this is good. If you have large models, you can't always send through all the variables, like in machine learning. So the interesting thing, let me go down a little bit. What is also clear, I think, is, or let's say to demonstrate what this charity does, is if we have our function here and all it does is it returns square root of x. I mean, we could just directly take this function just for visibility. And we can run this now in eager mode, right? Remember eager mode, where normally there's no decorator, it's TensorFlow, NumPy. If you give it a TensorFlow, Tensor, NumPy just takes it, makes it array. Fine. Well, if we now create a TensorFlow function, we decorate it basically, we just use the decorator explicitly, and we want to give that in, this will raise an error from NumPy, because NumPy now didn't get, of course, the value anymore, because inside this function, when the x comes inside, this is now a symbolic tensor, which is the whole tracing, right? It's decorated, so it doesn't execute it immediately, but it gives symbolic tensor, and NumPy doesn't know how to deal with that. So we could also be a little bit with if conditionals and stuff. This, of course, doesn't work either. And we could use the autograph here, but this is really a feature. If you're interested, you can look at it. It's not so relevant. I've put here a small thing on performance. It depends. You can play around with it if you like. There's different number of events with NumPy and tf, some function. We can compile it. We can measure the time. Let's say they're in the same speed. Usually, if it's a really good parallelizable, then TensorFlow turns out to be quite faster. Also, if the problem is larger, for smaller problems, NumPy is faster. But let's say NumPy and Numba and TensorFlow and the JIT of TensorFlow is on the, let's say, same order ratio of magnitude. I mean, as we can see, if you use now the Numba and the tf.func are, yes. So this is the compilation up here. So if you want to see the results, then you have calculate NumPy versus calculate TensorFlow. They're both eager. So TensorFlow, but it's a very large thing. It's 10 million. It's like a factor of 2 faster in the eager. And for the compiled version, TensorFlow is all around a factor of 2, 3. But this is 10 million, so you can make it smaller, and NumPy will be faster at some point. As I mentioned, there is control flow. You can use stuff like conditions. You can steer it out. There is also the possibility to declare gradients, which is not so important how to do it. And there is also already a lot of TensorFlow probability, for example, libraries that build statistical stuff on top of TensorFlow. The nice thing about this is that it's very consistent because it does all with TensorFlow. And the interesting thing now is this. We've seen this eager mode, and we see how we can just go with NumPy. Sure, if you use NumPy directly and combine it with eager mode, we can't use anymore the graph stuff and combine it, but okay, sure, that's the price you pay. What we can do always, just keep this in mind, you can always build some wrap it with a PyFunction. Set is, by the way, the wrapped backend in zfit. This is basically TensorFlow, just wrap. And we can always do this. This also works inside TF decorated function, but most interesting are these two switches, which make the gradient off and switch to a numerical gradient and the graph mode off. So what we can do now is this piece of code. We can implement an unnormalized PDF, and what we need to do here is to say we should assure it executing eagerly. This should fail if you want to do this in graph mode, because then all the NumPy stuff should not work and all these things. This can just go wrong. We say, okay, this is something I can just run eagerly, but fine, we can do that. And then we have here implemented our own Gaussian, and we can, of course, as before shown, instantiate it and compare it to the Gaussian implementation itself, and we get the same results using fully NumPy, meaning that we do not lose anything by, meaning we have TensorFlow, sure, but actually we're fully compatible with the whole NumPy, and we can use any kind of Python dynamic stuff we want. Any kind of Fortran function that you want, you can just put it in there and it works with zfit. Sure, in eager mode, but that's a little bit the price you pay, because sure, you cannot just like have everything compiled that you didn't write yourself in TensorFlow and so on. So to close out, I talked about TensorFlow and also compared with NumPy, and the conclusions to make, or the differences there that I see is, first of all, I want to say, I mean, Numba is a great thing and has a larger scope than TensorFlow. TensorFlow is more narrowed. So there are certain use cases for TensorFlow, but there are things where TensorFlow is just not fitted. What I like about TensorFlow is that it's very self-contained. So you don't use Python. You don't need to think, oh, can this if be compiled? I tried with Numba and I ran into so many issues because it didn't support lists and anything. TensorFlow supports everything. Simple rule is just TensorFlow operations are recorded. This means also that every dynamics that you want to have, every computation is with the API of TensorFlow. And this is very well designed. It's optimized. It's built with graphs in mind. NumPy wasn't built with graphs in mind or static and doing JIT and stuff. So that's why there's only a subset and all. And TensorFlow is a very well contained ecosystem in this sense. What it surely do, if you have many conditionals, if you have a lot of Python code in something, like shown with uproot, and then Numba is perfectly great. But if you have well-defined computing that you may need to stick together, that you need to run repeatedly, that's where TensorFlow, and which is also highly parallelizable, that's where TensorFlow really shines. The benefits of zfit, of TensorFlow 2.0 for zfit is that with the graph, we have very high speed, and with the eager mode, we have the flexibility. So a little bit the best of two worlds. One small example that was provided by Flavio is because he played around a simultaneous fit with 50,000 events or something that I just measured. This is not, the numbers aren't like taken for granted. It's just to give an idea and then compared with prop fit, which uses the Cyton and stuff, just to get an idea for the order of magnitude. And with eager mode, meaning the full flexibility, zfit is the same, it's just prop fit, while if it's compiled with the graph mode, which means a little bit less Python flexibility and just TensorFlow operations, it's around the same level of riffing. And that's the great thing about it. It's combining these two worlds, but basically using one framework and one backend. One question that could really be asked now in the end is basically the conclusion of everything is, why TensorFlow and not just Numba and NumPy? I mean, the performance seems similar in all the things. Firstly, that there is no Python compilation and we can just wrap anything with a tf.function decorator. And now that only the Python, only the TensorFlow operations are touched is very powerful, because it means we can have thousands of code just for accounting, just for adding the operations together. Yeah, maybe it takes a little bit more code, but it's very clear what is going on. And it's a very consistent ecosystem, like SciPy and stuff, and it's all the things that work well together, but I think with Numba and so on, in my experience, and as far as I know, there's always certain compatibility issue. You cannot use everything just like that. But TensorFlow probability is fully written in TensorFlow, so it supports all the features there. Furthermore, the graph, the grappler that takes a lot of these low-level optimizations and stuff like parallelization, it moves it to the GPU without extra arguments and all these things. And that's something that I find is very hard to produce ourselves, this kind of optimization. And in the end, still an important point, I think, is it's very well supported in the industry. And by Google, they're doing a great job there. They're developing a lot of stuff is going on. That's where there's money. There's a lot of debugging. There are over 130,000 stars, which means it's a very well-tested product as well. So that was my talk. Thanks for your attention.
And thank you, Jonas, for taking the time to browse us through this, given the work that you have put into understanding it in the first place. So we actually reached a nominal time, but I think we can spare a few minutes certainly to discuss a few things, a few of the questions that you got. I can share them to you. Give me a second. So I'm overriding you, if I may. You can probably read it. Some of the questions are long, so let's go through.
Yes. Yes, so that's a very good question actually on PyTorch, and this was also in the beginning a very strong thing on what you should use and not. One thing is that TensorFlow has more or better features for math, complex support, sparse support. I think Josh can also highly confirm this, where PyTorch doesn't have many of these optimized things. The other thing is then PyTorch is also moving from the eager to the compilation, which means you expect the API and everything to be better in TensorFlow, which started with the static compilation. In the end, the main question is, this is a different backend question that I usually answer in a similar manner, which is, it is great to have that, but why do you need it? It's like having a second car that does the same purpose and everything. Sure, if you can afford it, if you have developers that maintain all this, because more maintenance, you have to think double it, you have to do all this stuff. What do you gain? And if the answer is maybe a speed up of a factor of 2 in some cases, then it's just not worth doing it.
Mm-hmm.
So the next question,
can you read it? So it's just or
yeah. So yeah. So okay, yeah. Of course, you're right on that.
they're not easy, yeah? No.
Yeah, so I can read, yeah, from Jim, and yeah, I made this comparison more from a user point of view. I think behind the scenes they are somewhat different, as in, let's say, what TensorFlow graph itself, just a graph does, is on an object level. So they build a graph of Python objects, and they don't go for the Python bytecode, and then at some point they lower this graph representation to something that they call it MLIR, but this is, I think, merged also into LLVM and stuff. But they also mess behind the scenes sometimes very heavily with the Python code around, not the bytecode, I think. They do some stuff there as well. But I agree, behind the scenes, the things work quite differently, which is, I think, one of the strength points of TensorFlow. It has still this high-level representation of tensor objects together. So you have this graph representation, which are high-level Python objects.
Mm-hmm. So
you mean
the first line again? A question on comparison between TensorFlow and JAX. Yes.
So JAX is clearly the younger product, and what has to be said there, I think, JAX is still regarded a research project. It is not, doesn't has even close to stability or stuff that TensorFlow has. It's a younger project, and there are differences, but so for some things it seems that JAX is better, for other not so much. In the end, I haven't found like JAX is that much better. For some things it really is, but for others it feels a little bit like, so it's something to consider, but currently, let's say, it's not in a I think stable enough state to do. And one of the things is also that JAX uses directly NumPy, which is something I really like about the TensorFlow API. It is designed to be converted to a graph. So, you know, you can just do whatever it allows you to do. And NumPy feels sometimes I have to think what is actually possible or not. Yeah, exactly. So Henry's question, I think. So, yeah, so exactly. I think we talked about this. There is no ufunc in this sense that it overrides it what PyTorch does. So no, it does not. And to get the advantage of tf.function, you need to use TensorFlow math, yes. Which is tf.function, let's say, freezes all your code. It executes it once, all the Python code remembers that, but just remembers the TensorFlow objects. So in this sense, if you want to think about it, I think it's a good idea to distinguish between Numba and so on. It's really TensorFlow just puts together its tensor objects to build one graph. And this is what it extracts from a function. So it just runs a function to figure out which tensor objects have been touched, and that's what it gets.
Yeah.
But I mean, this, sorry?
No, fine, sorry.
It's in a way of, it has to be like that because, I mean, a JIT compiler has to be specific to something. It has to know what it has to compile. And I think Numba is way more generalized. Numba supports Python and NumPy and so on. So, and TensorFlow has more of its narrow scope that says, okay, we do the TensorFlow stuff. And a little bit of Python converter as well. Just convert some of the Python stuff to NumPy with autograph, but that's a different topic.
I see there's a lot of messages on the Zoom chat. Let me stop sharing. I would suggest that we continue that on the Slack channel on fitting statistics, because then anybody who was not available here, for example, can still see that, whereas here all of these messages will be lost as when we close the meeting. Okay, so let's continue that out in Slack, please. Other than that, if there's nothing pressing, yeah, let me thank again very much everybody for this super interesting session.